Today we will be solving this problem called sliding median. So we are given an array of n integers and our task is to calculate the median of each window of k elements from left to right. And the median is the middle elements when the elements are sorted. If the number of elements is even, there are two possible medians, and we assume that the median is the smaller of them. So basically here, this is the first window. It contains 3 elements, and if we sort them, they become 2, 3, 4, and the middle element is 3. That's why we outputted 3 here. We'll go through this example. Let's just recall that n can be as large as 2 times 10 to the 5th, and the values can be as large as a billion. K, of course, is between 1 and n. So let's go to the drawing board. So this is our example. Let's try to solve it by hand first. So the first window is this one. And if we sort these elements, we get 2, 3, 4. So the middle element is 3. So we write it down here. And then we move on to the second window. If we sort it, we get 3, 4, 5. And the middle element is 4. And so on. This is the other window. If we sort it, it is already sorted. So the middle element is 5. And then if we go here, if we sort this window, we get that the middle element is again 5. And if we move on to this window and sort it, we get that the middle element is 2. And finally, if we take this window and sort it, we get that the middle element is 1. And that's the answer, 3, 4, 5, 5, 2, 1. And in general, if we have an array of size n, the median will be at position n minus 1 over 2 if it is a 0 indexed. So here, like in this case, if this is our array, its size is 3. 3 minus 1 over 2 is 1. That's why we look at position 1. So this is for this example. Now we're gonna present the solution, and we'll present two solutions here. There is the first solution is easy to implement, but requires advanced data structures, and the other one is rather tedious but doesn't require any advanced data structures. So for the easy approach, it relies on a data structure that we saw before when we solved the Josephus problem 2. And this data structure is the ordered set. It is not a part of the standard library, but it can be obtained through GNU. And let's check it out. So here is an article that I will link in the description box that describes this data structure. It is a policy-based data structure. So ordered set is a policy-based data structure in G++ that keeps the unique elements. Notice here that the elements have to be unique, so it does not accept duplicates in sorted order. So far it does what a set does, but it performs all operations as performed by the set data structure in the standard library in log of n complexity, and performs 2 additional operations in log n complexity. Order of key k. So for example, if we insert elements 1, 2, 3 into an ordered set and we ask for the order of 1, it would return 0. It returns like the index of the element as if the set was an array and it was sorted. And the second operation is find by order, and it returns the kth element in a set counting from 0. So now everything starts to make sense. So what we need for this problem is to find this position in the array, and we could achieve that with an ordered set. So basically all what we need to do is, so we'll just declare our ordered set. So let's call this our ordered set. And since it only accepts unique elements, we saw this trick before, we would not have an ordered set of ints, but rather of pair of ints. And if we link each element with its index, then they become unique. So we'll just insert our k first elements into our set. So we'll insert 2 along with its index 0, 4 along with its index 1, and 3 along with its index 2. So since this set keeps elements sorted, they will actually be sorted in our case here. So they will actually be in this order. So let's just write this down here. So we have for 1, and we can ask, as we saw here, we can ask, we can perform this method find by order. So if we ask for this first window, if we ask find by order and give it the value 1, as we said here, it will return this element. That's, and we'll just print it. Then when we move to this position, it's like erasing an element and inserting another element. And as we saw in that article, these operations are performed in log of n. So we'll just erase this element and insert the other element 5 2. And in order to keep things sorted, I will just bring this here and insert 5 2 into 5 3, sorry. And here again I will ask for the element at position 1, and it will return 4, and so on. You get the idea. Let's do just one other interval and move on to the implementation. So for this interval here, we'll have to erase 4 for 1. So we'll erase this value and we'll insert 8 4. So in order to keep things sorted, this comes here and this comes here. So basically this data structure saves the day as if it was designed for this particular need. But I don't think that was the intended solution for this problem. So this is just some heavy artillery that may or may not be available in all contests and all platforms. So we will present another solution that does not rely on this kind of advanced data structures and just uses the data structures available in the standard library. So let's check out the code. So this is sliding window or median, sliding median, easy. Okay, so we'll start by reading n and k, then we will declare a vector of ints that will store our values. We'll scan them, then we will declare our ordered set, and it will be of type pair of int. And we can do this because in our declaration here we defined it as a template, so it can take any type as long as this comparator is defined for it. So let's go through the includes again. We have to add 2 includes, the 3 policy and this associative container, And we also need to use this namespace to use these without adding the namespace. And here it is basically this ordered set is a red black tree, and it takes this type t that can be anything, in our case a pair of int, and this is the second value. Since we have a set, we don't need a second value, but we could have something like an ordered map or something where we would require the second value. This is our comparator, so we need to keep things sorted from smallest to largest. That's why we used less here. We could have used the greater instead. And this is the type of tree we use for this, and this is red black tree, and we use, as an update, we use the 3 order statistic. And so that's pretty much it for the ordered set. So we declare our ordered set and we'll call it window. Then we will loop through our first window, so from 0 to k. We will just insert the first elements, like this is for initialization, and we will just print the answer for the first window. So we'll just print window dot find by order, and as we said, the index of the median will be at position k minus 1/2. And since we inserted pairs, the value along with its index, then we'll just print the first. Then we'll proceed to print the values for the other windows. So we'll have a for loop that will go from 1 to n minus k plus 1. And what we need to do is to erase the first element, the element that we just left. It will be at position I minus 1. So we erase values at position I minus 1, I minus 1, and we insert the next value, and it will be at position I plus k minus 1. And the magic of the ordered set will make everything sorted, and we'll just ask for find by order again and just print it. So that's pretty much it. Life is easy using advanced data structures. So let's just submit this. It doesn't feel like doing much. So it got accepted. Now let's move on to the actual tedious way of doing things, of solving this problem. Okay, so in order to solve this problem without using any advanced data structures, we'll just think about this problem first. So basically, we will keep having windows, and each time we want to print the median. So we have a median here, there is something to its left, and there is other values to its left, and there are other values to its right. And each time we will, after moving the window, each time we move the window, it's like we're gonna erase a value here and insert another value here. So the value we're gonna erase may be here or maybe here, and we will know where it will be. So maybe if it was here, these values will shrink, and this value will not be the median anymore. It will become this will become the median, because this is not equal to half anymore. So we will have to adjust for that. Or maybe the value we erase will be here, so this value will become the median, so we'll have to adjust for that. But in all cases, it is just a matter of erasing one element, inserting one element, and adjusting the size of these two intervals, or of these two, the elements to the left and to the right. And in order to keep things dynamic and sorted, we will use sets here. So how would we approach this? So we will have two sets. So we'll call one like left set and the other one right set. And we'll say that this left set contains our median. and it will actually be the greatest element in the left set. And we can access that greatest element using our begin or reverse begin. So reverse begin returns the largest element in the set. Okay, so how could we do this? So first of all, we'll start by taking this first window, and as we did before, we're gonna take each element with its index. So we're gonna have 2 0 4 1 and 3 2. We'll sort them first. So we're gonna have 2 0 3 2 and 4 1. And as we said, we're gonna have two sets, a left set and a right set. And we said that our median will be part of our left set, so our left set needs to include all this, while our right set will only include this value. Okay, so we'll insert these values into our set. So let's move this down a bit. So here we'll insert 2 0 and 3 2, and here we'll insert 4 1. Great so far. So now if we want to print the answer for this first interval, we'll just query the right begin the reverse begin of this set, and it will give us 3. So we'll just print 3 here. And now let's see what happens when we shift our interval to this. So basically 2 will be erased from this set, and 5 will be inserted into one of these sets. We'll see about that later. So basically we'll ask ourselves, we will ask if 2 0 belongs to the left set or the right set, and that's easy to perform. We'll just use a method like find on a set and we'll check if that's equal to the end of the set, or we can use count to see if it returns 0 or 1. So we'll check if count of left set with 2 0 returns 1. If that's the case, it means that 2 0 belongs to this set, so we'll just erase it. Otherwise it would have belonged to this set, and then we'll erase it from this set. And then our next value is 5 2, and now we ask ourselves, or should we insert it into this set or this set? So we'll just compare it with the reverse begin of this set, and the reverse begin here is 3, and since 5 is larger than 3, then we'll insert it here. And to keep things sorted, I will move this one up and I'll insert 5 2. But now we've broken the equilibrium, because remember, this needs to be of size 2 and this needs to be of size 1. So since it is not the case, since the size of this one is 1 and the size of this one is 2, then we need to make adjustment. We will keep moving the smallest value from this set into this set until the size of this one becomes 2 and the size of this one becomes 1. So we'll just take this element, move it up, and bring the smaller element from here into here. Now the size of this element is 2, the size of this set is 2, and the size of this set is 1. And now that's good. So we just query the reverse begin of this set and it gives us 4. Moving on to the next window. So now we have to erase 4 and insert 8. We'll erase 4 from here and we'll insert 8 3 into one of the sets, and it will be the right set because the reverse begin here will return 3, and since 8 is larger than 3, then we'll have to insert it here. So we'll insert 8 3, and once again the sizes do not match. The size of this one is 1 while the size of this one is 2, and it should be the opposite. So what we'll do, we'll keep moving the smaller value from this set to here until it becomes 2 1. And one might say this might take too much time, like in terms of complexity, but remember, before we erased and inserted element, these sizes were fine. This was 2 and this was 1, and all what we did was a -1 here or a -1 here and a +1 or +1. So it is just a matter of 2 elements. So at most we'll have to pop 2 elements and insert them here or something like that. So at most we'll be erasing and inserting 2 elements, so it's no big deal. So moving on, we said that we'll take this element from here and move it over here. So now the sizes match again, perfectly balanced as all things should be. So now again we query the reverse begin. It gives us 5, so you will write it down here. And moving on to the next interval, this is our next interval. We sort it, so we don't need to sort it, we just erase this element. So we erase this and we have to insert this, and notice what happens now. Now we ask ourselves, is 1 smaller than reverse begin of the left set? And the answer is no, so we just insert it here. Insert 1 4, and we'll query again the reverse begin, and it's gonna give us 5 again. So no additional work to do here. Now we will move our interval again. So now we have to erase this 5, and we'll have to insert 2. Reverse begin here is 1, so it is smaller than 2, meaning that we have to insert 2 here, 2 along with its index 5. And since the sizes got mixed up again, so we need to bring this one here. And moving on to the next interval, we'll have to erase 8, so we'll erase this value, and we'll have to insert 1. And notice what happens now. We'll insert 1 along with its index, and now the size of this is 3, which is too much, and the size of this is 0. So we'll keep popping the larger element from here and bringing it to the other set. So we'll bring this here, and now they are balanced, and we'll query the reverse begin of this set, and it will give us 1. I forgot to keep writing this, so this was like 2, and finally we got a 1. And that's how we obtain our answer. So basically all what we did was using 2 sets and keeping track of the size of this set and how they should be, and moving at most 2 elements after each iteration. So let's check out the code, but before we do that, let's mention something. Imagine that the size of our window was 1 instead of 3, then this right set will always be empty, something like that. So we might run into trouble. When we check for reverse begin. Maybe the set will be empty, and in general, since the window is just 1, we'll just print the actual value, the actual array as it is. And the same will happen if the size is 2. Then we'll have these sets will each contain 1 element, and maybe both elements will be in this set, and when we query the reverse begin, we'll have to check first if the set is empty. And in order to avoid all headaches, we will treat cases when k equals 1 and k equals 2 separately. And for the case when k equals 2, so our window is just these 2 elements, and the median will be just the smaller of the 2. So we can just print min ai plus 1, something like that. So that's pretty much it. Let's check out the code. So now sliding window hard. Okay, we'll start by reading n and k again. We'll declare our left and right sets, and we'll declare a vector of n to hold our values. We'll loop through all values from 1 to n. Then we'll manage those special cases we mentioned. When k equals 1, we'll just print the array as it is and return. And if k equals 2, we'll just print the mean of every 2 consecutive values and return. And then let the fun begin. So otherwise, we'll declare a vector of pair of ints. This is just the pre-processing we need to do at the beginning to know which elements we will insert into the left set and which ones we will insert into the right set. We could insert all of them into the left set and keep popping the largest element until the size becomes as we desire, but I just did it this way. So we'll sort them, we'll push the first k elements into our vector of pairs, and then we'll sort them and we'll insert k over 2 plus k mod 2, like the first half up to the median included into the left set, and we'll insert the rest into the right set. And I will query the reverse begin and just print that. So that would be the median of my first window. Then I will keep sliding my window, and each time I will erase one element and insert another one. So I will be erasing the value at j minus 1. So I'll check if it belongs to the left set, I will erase it from there. Otherwise, I will erase it from the right set. And then if for the value I'm gonna insert, I'm gonna check if it is greater than the reverse begin of my left set. If it is not, I will insert it into my right set. Otherwise, I will insert it into my left set. Then, while the size of my left set is less than k over 2 plus k mod 2, like this would treat the case if my left set is smaller than what it needs to be. Then, as we said, I will keep popping the smallest element from the right set. So I will get that with the right set dot begin, and I will erase it from my left set and insert it into my left set. And then I have to treat the case where the left set is larger than what it needs to be. In that case, I will just take the largest element from the left set, and I will obtain that with the reverse begin. And I will erase it from my left set and insert it into my right set. And after doing all this, my two sets will be perfectly balanced. Then I will just print the element indicated by reverse begin, and I'm printing the first there because that's the value. Second is actually the index. So that's pretty much it. Let's go ahead and submit this too. So that worked as well. Thank you very much for watching. See you in the next video. Bye bye.